Okay, great. Thank you very much for this kind introduction, and thanks to all of you for showing up. Because I mean, I gotta admit, the stuff I'm talking about is gonna be a little bit less catchy than, for instance, training Space Invaders with a neural network. So I'm a PhD student at the Neural Information Processing group at the TU Berlin with Professor Klaus Obermeier. And usually I deal with the simulations of neural networks, but now, or today, I'm going to talk about a little Python toolkit I've been developing on the side, which is called pypet. And so if you find yourself in a situation like me, that you deal with systems that are highly parameterized, so for instance, I simulate parts of the brain, or you do some machine learning pipeline or develop a new machine learning algorithm that has like tons of hyperparameters, then you have such a highly parameterized system. And sometimes what you want to do is not just run it once, but with different parameter settings, so sample from this high parameter space. And then later on, look at the results and analyze them like very coherently. And so if this somehow applies to you, then this tool can help you in doing this. So, but let me first start out with sort of the motivation here, why I came across developing this Python application. So let's say this is the ideal circle of numerical experiments or simulations, or if you start prototyping some application. So basically you start out with a rough idea or a hypothesis about what your model is about or what it should do. And then after like planning ahead, you start implementing your model, you start coding, and once it's done, you of course run your model, you gather some results in your simulations, and this helps you to refine your idea and see if your hypothesis actually works out. And then with this, you can again improve your coding, run new simulations, and basically go in this circle over and over again until, I don't know, like a scientific publication pops out or you have a super cool machine learning application. The only problem is that is a very idealized world, because if you look at the ground truth here, so you start with an idea, it's like, yeah, let's just hack something together. So let's just get it running quick and dirty. And of course, I need to run my system with different parameter settings. So okay, I got my Python script here, so I got to start it again and again with different settings. So the simplest thing I can do is, for instance, do some bash scripts that restart my Python executable quite some time. And of course, this churns out some results or data, which I somehow need to serialize and store to disk, for instance, using Pickle. And then you end up with, I don't know, like hundreds or thousands of files, which you later on need to analyze. So you write some other hacky I/O that somehow reads your data, and you can then make some nice matplotlib plots with it, and see if your idea worked out, and maybe not. So you write some more spaghetti code, and you go in this circle. This works fairly well as long as you go forward. That's because at some point you might realize, okay, there were some ideas in the past, maybe 2 months ago, which weren't actually so bad. So maybe I should look back at the simulations or results I gathered 2 months ago. And if you go in this circle and you think, okay, maybe let's repeat an old simulation, you might miserably fail. And in the worst case scenario, you're not even having your source code under Git version control. So this is really doomed to fail. Yeah, you're laughing now, but if you talk to scientists, there's an awful many of them like who haven't heard about Git yet at all. So and their versioning is like my MATLAB file version 1, my MATLAB file version 2, my MATLAB file version 2.1 from yesterday or something like that. So if you go around this and you try to repeat an old simulation, this doesn't work. So it's kind of sad. It's also getting worse if someone else, like a colleague of yours, comes along and tries to understand what you did here because he thinks you got some neat ideas in the first place. The only problem is, so this is hard to tackle then for him to actually understand what you did. So this is where my toolkit comes into play. You see everyone's happy. So pypet basically tackles the both points down here. So the parameter exploration bash scripts that are no longer needed, or like nested for loops in your outer main script. And also it provides some I/O functionality that automatically stores your data. So I mean, if you write bad code, spaghetti code, no one can read. This is still your own problem. So what does pypet stand for? So it stands for Python Parameter Exploration Toolbox. And as I said, it's suitable for any sort of numerical simulation that you run in Python, or at least start with a Python script. So as I said, so the main objectives of this toolkit are easy exploration of highly parameterized spaces or models with a high parameter space, and easy storage and retrieval of the computed results and the underlying set of parameters. So a tight linkage between the parameters you use to run your model, whatever it is, a brain simulation, a machine learning pipeline, so that these parameters you use to obtain your results, your accuracy or your time series data, this is like tightly linked, and you can always see, okay, this was the set of parameters I used to gather these numerical data. Okay, so how does it work? So it evolves around a new Python container, so which is called trajectory. So it's basically a more sophisticated dictionary, or to be precise, like a nested dictionary. Because it implements sort of a tree data structure, and it manages all your parameters and results. So for instance, we have this function here, f at parameter. So this prefix f here, I stole the idea from PyTables, that these functions of these containers that actually do something for you start with an f underscore, so you can actually distinguish them from data you put in there. So for instance, we could add a parameter here. We give it a name like traffic.nCars. So this is the name of the parameter, and this is a particular group. So for instance, it's the number of cars in a traffic simulation. So we give it a default value, and you can always provide a comment so that other people understand the scope of your parameter. We could add another parameter that belongs to the very same group, and it's the number of cyclists. You give it a default value. You can add a comment, and we might have, for instance, some more meta parameters, like a step size of your numerical integration system or whatever. And when you do that, of course, you can recall the data because this is a container for all your parameters. So eventually, in your simulations, you need them to actually do stuff with them. So for instance, you can then recall the data you just put in by this dot notation. So you can just say like tray.traffic.nCars, and it just gives you back like the value we put in there. So as a user, you're encouraged to actually fine grain and sort your parameters as fine as possible. But in order to save you some typing, so you can skip intermediate hops in this tree. So you could say, for instance, tray.cyclist, and this will initiate a very fast lookup if this is a unique identifier, and you get just immediately back the value of this parameter. So it's rather permissive of stuff it swallows. So the thing can handle all sorts of Python natives, of course, bool, int, float, Python containers, and also likes Numpy arrays, matrices, Scipy sparse matrices, pandas, DataFrames, and series and panels, of course. If you are into computational neuroscience, you might have heard about a simulator called Brian. So it also likes quantities and monitors of this software thing. And in brackets here, basically you can chuck everything in there that you can pickle. But I put that in brackets here because if you do that, then you don't have any chance to eyeball the data, because reading pickle strings is not nice. And if you work with anything else, so there's a very simple API that you can just extend and make it work with data that you have. So as I said, the other objective here of this trajectory is to allow arbitrary explorations of the parameter space. And this is why this container is called trajectory, but because it doesn't hold just a single parameter value, but you can give it like a whole trajectory through the parameter space that defines on how you run your model. You can do some arbitrary exploration. So because we had, for instance, our two parameters, number of cars, the number of cyclists, and you try to explore the space like this, so like this simple Cartesian product space, or a line, or whatever comes to your mind. And as I said, another objective of pypet was to store the data right at hand, so you don't have to touch the I/O. And currently, so everything you chuck into such a trajectory container is automatically stored to disk, and the current backend is HDF5. I guess some people of you have heard about HDF5. So it stands for the Hierarchical Data Format version 5, which is a very neat file format because it can store massive amounts of data. It can read and write pretty quickly, and still it's human readable. And so if you, for instance, look in such a file, you can see here there's this file and folder structure with these leaf nodes, and you can click on them and immediately eyeball your data, which for prototyping and scientific applications is usually very useful if you can immediately see if the values kind of fit of your expectations, or if you already have a bug somewhere that already pops up by some numbers that can't be true anyway. So in order to interface HDF5, pypet uses the super great pytables library. Okay, so this is the basic data container that's provided by pypet, this trajectory. There's another object you can interact with, and this is called an environment. And this is basically a Python object that helps you to disentangle your core scientific or prototyping simulation from the I/O management and the execution. So for instance, it does stuff like it manages creating log files for you. It nicely integrates with Git. So if your code base under Git version control, what it will do is it will either complain if you try to run a simulation with new code that hasn't been committed yet, or if you wish, it will just start an automatic Git commit for you and add the comments to your trajectory as your Git comment. Also, you can do, you don't have to specify the way you want to explore your parameter space in advance, so you can also do some adaptive exploration, and if you have some search heuristic, you can combine it easily with pypet. So for instance, if you know the deep library, you can use evolutionary algorithms, for instance, to search the space. Also, it natively supports multiprocessing because it's basically, I mean, you run a couple of simulations in parallel, so a couple of simulations that are independent, so it's clear that this is super easy to parallelize. So natively, it supports multiprocessing on a single machine, but if you combine it with the cool Scoop library, you can also use that on a cluster like an SunGrid engine, for instance. And just let me show you a quick live demo, although you're always told not to do that. Okay, so let's say we have some particular task or simulation at hand that we want to do. And here, let's do something very simple. So let's just say we simulate the multiplication of two numbers. It's a fairly easy task, but I think it serves as a straightforward example. So let's say we have value z, and our top-level simulation function here does take this new container trajectory, and we can, of course, access everything by dot notation. So we can say our new value z is equal to tray.x times tray.y. And of course, we want to store the result and add it also to the trajectory. So we have to say, tray, please give me a result, or add the result under the name z with the value z, and that's about it. So this would be, so usually you would do something more sophisticated here, I don't know, like a neural network simulation, as I said, or super cool machine learning. But here, let's just multiply two numbers. So, and the only thing now still missing is some boilerplate code that actually runs our simulation. So we can say, please pypet, give me one of these nice environments. So we have to create that one. And this one will also provide this trajectory for us. And now we still need to fill the trajectory with the actual parameters. So we can say, please add the following parameters. So we can say x, give it a default value, and maybe provide a comment. So this is the first dimension. And also we have a second one, which is y. And now we specified that we have two parameters with default value 0, but we're actually interested in exploring the space. So what happens if we multiply two numbers? What happens if we multiply 4 times 3, for instance, and not just 0 times 0? So we can tell here simply in advanced, simply in advance how we want to explore the space. It's pretty simple. You just pass this container with this function fexplore, a dictionary of lists, which just gives you the way you want to explore the space. So for instance, we choose x should be 1, 2, 3, 4, and y should be, let's say, 3, 3, 3, and 4. So this will explore as just these 4 points, 1, 3, 2, 3, 3, 3, and 4, 4. And so if you had, for instance, the Cartesian product in mind, there are helper functions that can provide you with the Cartesian product, but let's stick to this simple example here. So in the end, the only thing we still need to do is tell the environment that with this trajectory, we want to run our particular simulation, which is multiply. And now this should run, and that finished pretty quickly. And because we just multiplied 4 numbers. But if we now look at the file system, so we have a HDF5 file here, which we can look at then, and it's a bit blurry. Can I increase that? Okay, but sorry, I can't zoom in here right now. But as you can see, so we got these 4 runs here, and for instance, the last one I think was 4 times 4, and luckily that's 16, so it worked. I'm glad. So okay, you can do live demos. Okay, so and usually what you then would do is later on when you gather your raw data from your simulations is you would fire up the thing again and then use this trajectory container to load data from disk and then do your analysis or plotting or statistics or whatever you have in mind. And so what is even more important about pypet, so it's, of course it's open source, it's available on GitHub, it's available on PyPy, it's fully documented on Read the Docs. And of course, it's thoroughly tested, so using Travis CI, AppVeyor, and I can probably say over 90% code coverage with more than 1,000 tests, so it's already quite mature. And that's about it. Thanks. Where to get pypet? So as I said, it's not only available on GitHub, it's also available on the Python package index, so you can simply pip install it. And it's pure Python. So if you have all the prerequisites, which are only a few Numpy, Scipy, pandas, and pytables, then you're good, and you shouldn't have to do anything, and this should finish within a millisecond. The documentation is online available. There's a very comprehensive tutorial, and also many, many examples. So if you're not the type of guy who likes to read manuals, that's fine. There's tons of examples how to use it. And now that's almost about it. There's some more bonus tracks. So I'm actually at the end of my PhD, and now I'm looking for a job. So I just bluntly use that situation to advertise myself. I'm looking for a job as a data scientist because usually I do this. So I stare at a bunch of differential equations and try to solve them and cry and then just numerically integrate them. But I would love to do, apart from that, Python coding, data science, or machine learning. So thank you very much. Thanks for your attention. And
so thank you for a very nice talk and also for being so courageous to start a live demo without any code written before. That's impressive. And yeah, so we have plenty of time for questions. Who has a question? Over there is first. Do I have anyone to do this? No.
So thank you for doing that, because I guess I'm going to use it. It looks very useful. And could you elaborate a bit about the structure in your trajectory, how you relate the trajectory of the parameter space to the data sets?
So you mean, so you explore the space and you create some data.
So how do you just store like, okay, I have z equals 2 as a feature for my simulation, and I just have this new attribute, or how do you manage that?
So the parameters in HDF5 are actually stored as a huge vector in there. So an array, just an HDF5 array. But the results are actually stored as single leaves, because you're not supposed to have, so you don't have to have the same result or the same type of result in every simulation run. Because it might be that you figure out during the runtime that something diverges, so you can immediately skip and you don't have to store anything.
Thank you.
More questions? There's one.
So you talked about having more sophisticated strategies for exploiting the search space besides lists. So is it possible to have this dynamically during runtime, like the Bayesian approach we heard of yesterday?
So the function optimization itself is not in there. So if you have your own like Bayesian framework that just takes some results and produces, I don't know, like a new probability distribution that you want to sample, then you can stick that in there. You can also already start analyzing your data while there still runs in the background. So you could, for instance, I don't know, like you have already start out with 20 different runs, and while the last 10 are still executing, you throw up your Bayesian framework, you calculate a new probability distribution, and I don't know, like draw 20 new runs, and you just add them to the running queue, and they will be executed eventually. And you could still then, in an interval of I don't know, like in the next hour, redo that while there's still runs executing. So as I said, the function optimization itself is not in there, but you can just plug it in and do the analysis during runtime and increase the run. So this is, for instance, if you have this evolutionary toolbox deep, there are examples how you can just plug in deep and let it do some search for you.
Who wants to go first? We have time for both questions.
So you already mentioned that if something diverges, you can just skip that result. I'm dealing with simulations that go for a very long time. Do you have any kind of crash management? So for example, if there's a power outage, is there a possibility to create a log file and like pick up from this point at a later time?
Actually, there is. So you could. So as long as everything that you have can be handled by a library that's called DIL, which is a bit more sophisticated pickling, then it can take intermediate snapshots, and you can pick up from somewhere where somebody pulled the power plug.
Hi. Do you think it'll be feasible to use just the parameter exploration space with other scheduling backend?
Yeah, I guess. So actually, regarding backends, so I'm now also experimenting because some people are not that happy with HDF5, so that you also could, for instance, use MongoDB. Yeah. And I was also, someone suggested using Elasticsearch in the backend, which then would make the distribution even more easier. But yeah, you could use the trajectory container, for instance, completely independent of this environment thing. Yeah.
Actually, I meant more like scheduling backend, like instead of grid engine, maybe Spark or multiprocessing or something like that.
So far, there's only the grid engine supported and multiprocessing. But you're happy to. I take contributions, implement that, make a pull request. Great.
Perfect. And just one very small question. It's more like a feature request. One problem which you see is that the heavy-duty core simulation function has to know of trajectories. I think it would be rather nice to have a helper function or a decorator which you can just plug into a non-pypet aware function and just pypetify. Does it make sense? Or
yeah, it makes sense. So I actually thought about this, having sort of like a general decorator that you just like attach to your function. So I love decorators when they are part of like a given library, but having the user putting decorators. So there are examples how you can wrap around Python around an existing simulation framework where you write your own wrapper function. I mean, this is going to be like 2 or 3 lines of code. Okay. So you could do that in a decorator, but I think then it's hard to understand how it works, the magic behind that.
Thank you.
Okay. More questions, or? Well, if not, then let's thank our speaker again.